At the Bowen Lab at Purdue University, it's time to get shaking. This test is designed to assess how these aluminum structures respond to earthquake-strength vibrations. They're what are called architected materials. Their shape is loosely based on a honeycomb, and they are engineered to absorb energy.
One thing about these materials that can be used for energy absorption, for protection. This could be, we are protecting somebody, we are protecting a structure, we are protecting a device.
With support from the National Science Foundation, engineers Pablo Zavatiri and Nilesh Mankame are working to better engineer energy absorption into materials all around us. This goes beyond constructing earthquake-resilient buildings. Think low turbulence air travel, safer sports helmets, even scratch and dent resistant cars.
So you hit a trash can and you don't have to pay a huge amount to repair your car. It should be able to pop right back and sort of save you the trouble of going to a garage.
The team works with smaller honeycomb-shaped test articles in the lab. They're technically called phase-transforming cellular materials. To understand how they work, start by thinking about how a spring works.
When you compress it, it goes down nicely and smoothly, and it comes back up nicely and smoothly.
The architected material does something entirely different. It snaps.
So it has the same or a similar structure where it has these beams going back and forth. But now watch what happens when I compress it. So the sounds that you're hearing are snapping off the individual beams in the sample.
The snapping releases or dissipates energy, just like a natural shock absorber. Afterward, it can be reset to resume its natural shape.
We can use that material. Basically, we have a snapping mechanism that remains completely elastic. The material doesn't damage. So that means that then you can use it over and over.
They can make architected materials out of lots of things, even concrete. One project in the lab is looking at 3D printing concrete to better control how it cracks on impact. They incorporate helical forms inspired by the shells of mantis shrimp.
When we 3D print concrete, we incorporate these forms in them. What we found was that this 3D printed materials can have higher energy absorbing capacity. They can have 50% higher toughness, yet at the same time they can be 50% more flexible.
To build better architected materials, the team is looking to the natural world for inspiration. They analyze all sorts of biomaterials under the microscope, testing what happens when they break. They've examined honeycomb and mantis shrimp, and also seashells, bamboo, woodpecker beaks, and much more.
The reason why we are looking at nature is because it's a really good example of how nature came up with really good solutions from the materials engineering point of view.
The materials they 3D print in the lab are by no means identical to a honeycomb or shell, but they incorporate some of the same forms and mechanisms.
If you look at nature, nature is a big natural 3D printer, right? So it's making layer by layer, it's trying to actually create things in a very different way than the way we have been doing it. So we have the capability now to place material in the right place according to the properties that we are looking for.
Taking bio-inspiration from the natural world, designing energy-absorbing materials to pave the way for a future that might not be quite so jarring. For Science Nation, I'm Miles O'Brien.